All right, welcome back from the break. Our next talk is by Florian Skopik, Markus Wurzenberger, and Max Landauer of the AIT, the Austrian Institute of Technology, with their talk, Don't Get Hacked, Get AMiner, Smart Log Data Analytics for Incident Detection.
Okay, thanks a lot for the introduction. Hello also from my side to the talk, Don't Get Hacked, Get AMiner. The next 45 to 50 minutes, we will have lots of fun with log data analysis and analytics. In the beginning, quick riddle. Some of you might know that slide from other talks, but it's a nice one, I like it. What do these things have in common, which are the Titanic, Helm's Deep from Lord of the Rings, Secret, the Dragon Killer or Dragon Hunter, the Death Star from Star Wars, and Achilles? And come to the solution, all of those had certain vulnerabilities, certain design issues, which ultimately caused them to fail, although they seemed to be invincible in the beginning. And this is very much the same for our networks today. As most of you know, it's often only a matter of time until a network gets breached, which means preventive security is important, but prevention ultimately always fails. So this is why in our research we focus very much on monitoring, intrusion detection, etc., to spot adversarial activities as early as possible in the whole kill chain, so that we can enforce some proper countermeasures. This is nothing new, of course, so this is pretty much state of the art, at least for more mature organizations. But the state of the art when it comes to monitoring and intrusion detection still is we mainly investigate network traffic with the common tools that are available. So we check if the protocols are sane, if the protocol headers are okay, and stuff like that. We do signature-based intrusion detection, so we look for known bad. We ingest log data from different services, applications, etc. into CM solutions, mostly use predefined roles to investigate them and to spot adversarial activities. And we only do limited anomaly detection, mostly outlier detection. So for instance, if a new protocol pops up or a new IP address shows up, this is something you get alerted on. But actually, there needs to be done much more than that. You need more anomaly detection to spot unknown attacks. And this is where our research focus lies on. So I mentioned some of the issues with network security monitoring today, and there are even more. One is the increasing use of encryption. Don't get me wrong, encryption is a good thing. It ensures confidentiality of data. It limits also the activities that an insider, for instance, could carry out. But it also drastically limits the visibility on the network. So encryption is a tough thing also for defenders because it's hard to understand what is going on in their own network if everything is encrypted. And we have TLS everywhere. Attackers, and we had this in the previous talk, increasingly live off the land, which means they don't use D1 hacking tool, something like that you can spot easily, but they basically use the tools, protocols, technologies that are native to and in the environment that they are attacking. And high-profile attacks often don't use technical exploits at all. They steal, for instance, credentials, they compromise a supply chain, something like that. So they don't exploit the technical vulnerability, so you can't actually spot the exploitation of a vulnerability. So there are no signatures that you could capture, and there are no rules that can flag malicious activities. So that's a problem, of course, and we solved that, or try to solve that, with anomaly detection, which means even if an attacker has legitimate credentials and he logs into a machine, logs into a service, a server, whatever, so like a legitimate user would do, he eventually behaves differently in that environment. So he doesn't use services and machines in the same way as a legitimate user would do in course of satisfying the typical business processes. And we use novel machine learning approaches to observe a system, how it is being utilized, and what is done on the system, and then dynamically build up in the training phase a utilization model and behavior model, a baseline, so to say. And whenever new events pop up that hasn't been seen before, or if a user behaves differently than from what have been learned, we learn on that. Of course, it's very important here to have visibility, which means we look at the endpoint, and we specifically look into verbose log data to actually learn what is going on in the system, and then compare what is going on in the system with what we have learned and trained before. All right, so intrusion detection from the beginning. Signature-based detection is what is commonplace today. In a nutshell, you have a list of known bad values, for instance, known bad IP addresses, like the IP addresses of a command and control server, or something like that. You know those bad values, or you need to know these bad values, and you look up your logs and see if one of these values show up in your logs, and if they do, you can be pretty sure there is something going on in your network. That is very efficient, that works well. The pity, however, is you need to know in advance what is bad, and that's increasingly complicated. Because that is complicated, you could do allow listing, which is quite the opposite. You define what is okay for your environment. So basically, you should know what is okay in your environment. For instance, what IP addresses are okay. And then you spot if there's anything that deviates from that allow list, which is very exact. You can also detect unknown attacks. However, it's complex and complicated to generate that allow list, and specifically to maintain this allow list. So this is why we do anomaly detection. We use machine learning to dynamically create this allow list and maintain this allow list. So we observe a system for a certain time period, check what values appear, for instance, in particular logs, add them to a model, and do this in a training phase, which goes here until the dashed line that you can see on the screen. And then in the detection phase, we spot whatever deviates from that trained model. That's, again, very exact. It can also detect unknown attacks. Of course, comes with its own challenges. So there are a couple of challenges when we process log data, because log data is very complex data. It's textual data. It's not simple numerical data. They have mostly unknown structure. So as you know, log data can look quite diverse. We come to that in a minute. Log data needs to be processed online, at least if you would like to do intrusion detection, which means whenever an event comes in, you need to decide right away, is that event okay or is it not? You don't have the time to look a second time. And that's basically one of the most, or the biggest challenges is you have a moving baseline, so because also your system that you observe changes. Because you apply updates, for instance, you add a service, you add a computer, you remove a network link, something like that. And we're working since a couple of years on solutions to tackle that problem, and today we're going to introduce you into two of those. A flexible log data parser, which allows us to parse the actual log data, but without defining endless lists of regular expressions or something like that, but a machine learning approach to do that automatically. And the second one is the actual anomaly detection on top of that parsed data, which goes beyond simple outlier detection. Okay, let's take a deeper, bit more technical look into that. There are lots of common log formats, but there's not the one log format, as most of you likely know. So for instance, you have here Apache access logs, where you can see already in that screenshot, at least somehow, there are some common structures. So you have a timestamp at the beginning, you have, for instance, an HTTP request method, you have complex URIs, tokens, session IDs, etc. This is log data. This is what we are going to process. Of course, this one is log data too. Might look similar in the beginning, but if you take a closer look, here you have key value pairs. So you have a key, an equal sign, a value, which is high granularity, you have encoded values, etc. So this comes from an audit daemon. It's on another level of abstraction. That one is log data too. That's actually JSON format. It just looks a bit dense, a bit ugly because we stripped out the spaces. But you have many attributes here, high volumes, log events go over multiple lines. You have system logs, they look entirely different again. They are very unstructured, they're human readable, which is good for humans, which is at the same time bad for machines. Diverse event formats. You also have implicit correlations. For instance, that log data tells you when a service starts, when it has been started, or when it stops. So there are relations between these events. You have DNS queries with specific user queries. Or, and that one is particularly of interest, you have application logs which tell you what a user did on a system. So for instance, here you could see a user logs on, a user sends a message, but also a user creates a task, delegates a task, uploads a file, stuff like that. And we are going to process all of those because we need to look into all of these data in order to spot adversarial activities, but we would like to do that with minimum human effort and with a minimum set of predefined rules or predefined parsers. And the solution that can do that, that is also open source, is ACID, and particularly AMiner is the component and implementation of ACID. You can see here a pipeline which consists of 3 steps. So we take input from various sources like Elasticsearch, for instance, where you can get the log data from, or a message queue like Kafka, for instance, a raw socket or raw log files. We take the data, we create the parsers, we parse the data, and then move it on to the analysis part. In the analysis part, we have different kinds of detectors. We'll come to that in the later part, how these work. And at the end, if we spot anomalies, so something that we have not seen in a training phase, we output an alert, again, via message queue, for instance, at the console or via email, whatever. One of the common setups that we have is we use that system as a sensor, as a kind of intelligence sensor for a CM solution, because the important point to get here is we don't claim that this solves all your problems and you need to replace your existing systems with that, but we say this is an intelligence sensor that can enrich your existing detection mechanisms. So this is complementary to the common CM solutions, for instance, or work together with that. So how does it work? We basically have 4 steps on a high level. We need to generate the log parsers, so there's no way around that. We need to dissect basically the single log lines, and we need a recipe on how to do that, and we can do that with machine learning, so we can identify common structures, for instance. We can identify what data types are in there, and so on. We need to do that in order to create hypotheses. So the self-learning system creates hypotheses, which means it makes some assumptions on what is normal for that system. Under observation, for instance, it says there are certain ranges of IP addresses at a particular part of a log line, or it makes an assumption of how events are correlated with each other, stuff like that. Then evaluates these hypotheses over a certain time span, and if that hypothesis holds, so if it is evaluated true for a couple of times, it becomes a rule which is then further enforced. So basically these rules constitute the system behavior model. With the rules that are great on the fly, I then know what is okay in my environment, and I can then alert on any deviations that I spot. So that's in a nutshell before we go into more details and how it actually works.
So thank you very much, Florian, for this introduction to the topic of log-based anomaly detection. As we already heard, the first part of log analysis is usually log line parsing, and this is also the part that my part of the presentation will cover. So log line parsing basically takes care of dissecting log lines into meaningful parts. It detects static and variable parts in log lines, and this information is used for assigning event types to the log lines and basically prepare them for further analysis. So traditional parsing approaches usually use lists of regular expressions that are iterated over until one of the regular expressions matches the current log line. However, this approach is quite inefficient when it comes to log analysis that is done on host level, where usually resources for analysis are limited. And when we consider the ever-growing volume of log data that is generated in modern networks, we need more efficient approaches. That's why we developed a novel parsing approach that uses a tree-like structure and therefore implements a single pass procedure. So this approach does not only allow us to efficiently process log lines, dissect them, detect variable and static parts, but it also allows us to efficiently access the information that is stored in each log line. So in the lower part of the slide, we can see an example of such an parser tree for NTP logs, and we can see that the model basically branches in specific locations and only a specific part for each log line has to be considered. On the left-hand side, we can see that it's possible to address the information that is stored in the log line using similar paths as they usually also occur in file systems. However, we have the problem that logging usually doesn't follow common standards, which means that each log source has a different structure and the log lines for each service are different. which means that usually in log data there occur thousands of different event types, and it's quite cumbersome to define parsers manually. That's why we need novel, efficient approaches for automatically generate such parsers, and that's why we developed the parser generator named ACID-PG. ACID-PG basically implements a density-based approach that is independent from semantics, which means it can be applied to basically any textual log source. Another problem with current traditional parsing approaches is that they often neglect major parts of the log lines, because log lines can be quite long, which means that the more detailed the parser is, the more inefficient it gets. But the parser ACID consumes the entire log line and allows to access all the information that is stored in the lines. So for generating the parser, we usually collect a sort of training data set, and first tokenize the data, where we use a set of different delimiters that depends on the log data at hand, and we use basically the transition frequencies between tokens for generating the parser tree and also for identifying static and variable parts in the data. When you look at the example in the lower part, we can see, for example, that the black tokens are followed by 50% by yellow tokens and by 50% by green tokens. Another important fact is that ACID-PG builds the parsing model from a local point of view. That is especially important when we have different services that log to the same log file, as it occurs, for example, with syslog. Their different logline classes should not influence each other when generating the parser. Another important feature is prohibiting overfitting, because it could happen that, for example, during the parser generator process, actually variable parts of the logline could be considered static, which would lead to the fact that the parsing model only fits the training data and could not apply it for further analysis. So here we can see an abstract example of the parser generator approach. What we can see is that the parser tree basically consists of three main types of nodes. So we have here nodes that allow static input, we have nodes that allow variable input, and we also have optional nodes that do not have to occur in all the log lines that match a specific path in a parser tree. We can see here also that the parser generator already sorts out some events that should be considered as anomalous or as outliers. So it's also basically capable to generate parsers for data that already includes some anomalous log lines. Yeah, here we can see an example of NTP logs, and this log data is quite simple. So we have only 3 different types of events here, and we can have a look at the templates basically that also would form the basis, for example, for generating a traditional parser that uses regular expressions. The variable parts are here marked by the paragraph symbol, and the parser approach we use also allows us to assign specific properties to the variables. So for example, some of them only allow integers as input, while others, for example, only allow IP addresses as input. So now we arrange the parser tree, and we can see that we have 3 different branches in this kind of parser tree, which basically relate to the 3 log event types that are stored within the data we saw before. So we then can aggregate some of the paths to sequence elements, which makes it easier to define the paths that basically let us to address the information stored in the specific nodes of the parser tree. So each of the sequences gets an ID assigned, and also all the nodes that occur in the parser tree. And using these IDs, it's then possible to define paths that basically allow us to access the information that is stored by the different nodes and can then be used for further analysis, where we will see some examples later on in the 3rd part of the presentation. So we can see that each of the paths basically consists of the IDs of the sequences that lead to the node, and we can also see that the end is marked by the ID of the node itself. Yeah, so now we will also see a short live demo of the parser generator. So I now will move to the command line. So first, let's have a short look at the data we will use for the demonstration. So we use here logs coming from an Exim mail service, which basically provides information on the SMTP protocol and stores, for example, information on incoming and outgoing messages. And as we can see here, it wouldn't make sense to just consider spaces for delimiters when generating the parser, but also, for example, equal signs, since they split key value pairs in this sort of data. So when we now have a short look at the configuration, we can see here that we have to define the input file, for example. So here we have the main log that I just showed you. And we can also see that we can define several outputs, and we will see later on that we also provide a visualization of the parser. We provide a file that basically can be used as the parser directly with the AMiner. And we also provide the log events that basically similar to the templates that are used for regular expressions in parsing. We can also see here that we have to define some thresholds that are used for generating static variable nodes and deciding where the model should branch. We have here also a damping factor, which basically takes care of prohibiting overfitting, since log lines are more similar in the beginning, so at the root node, basically, and are more diverse towards the end, which means that we have to adjust the thresholds a bit. So, okay, so let's run the parser generator now. So the parser generator is basically a Python script that is also available as open source on GitHub, but we will hear more about that a bit later. So we can see here that the data we process basically consists of almost 13,000 lines and holds 7 different kinds of log events, and the generated parser basically consists of 23 different nodes. So when we now look at the log events, so we can see here that we have generated 7 events that consist of static and variable parts, and we can also see the generated parser model, which is basically Python code that can be used by the AMiner. We can see here the sequence model elements, we can see the static elements, we can see some of the nodes only allow integer input, while others allow any kind of string. So we also generate a graphical visualization that helps to understand the generated parser a bit more easily than looking at the parser that can be used for the AMiner. And here we have, again, orange nodes contain static patterns, while the blue ones allow variable input. So maybe the last thing I want to show is when we, for example, would change the delimiters here and use only spaces, as it is usually done by traditional parser generators, and we run the parser generator again, we get a similar amount of log events. In this case, there are 7 different events, but most of them only consist of meaningless variable parts. So one benefit of the parser generator we use is that we can basically define different kinds of delimiters for generating the parser. So that was my part, and I now hand over to my colleague Max, who will talk a bit more about online anomaly detection.
Okay, thanks. Now we come to the final part of this presentation, which will be about anomaly detection and how we realize it in the AMiner. And first, a quick recap. You've heard before that there's this 4-step procedure of the AMiner, where the first step is parsing. We've just heard quite a lot about it. And steps 2, 3, and 4 are about generating these rules and testing for violations. So here's a short example. You see this line here, which says like accepted public key for backup from, and then a specific IP and some other parameters. And some rules that we could derive from this is that the user backup should always occur with this specific remote IP or with a specific fingerprint, or even we could take the timestamp into consideration and make sure that the backup user only produces logs in a specific time interval. How do we create these rules? Well, we could either brute force it, but just trying all the possibilities, or just a random subset, which is much more efficient. Okay, we realized these detectors in the AMiner by creating modules for them. So in the top you can see the AC toolbox, which provides all the modules, and at the bottom you see the pipeline of the AMiner. And here at the left side of this pipeline you can see the different input possibilities. We can read logs from databases, from message queues, from sockets, and that's the most convenient part, and also what I will do in the live demonstrations later on, just reading them directly from log files at the same machine where the AMiner is installed. We then parse the log data. For this we can either use some predefined models or the parser model generator that we've just seen before. Then this parsing already gives us a very simple detection, which is the log event parsable? Because if it is not, then something is strange, then either our parser is not good enough or a new event occurred. Assuming that we could parse the data, there are then a number of detection modules, and here we try to make some classes for each detection, like detecting new values or combinations, ranges of values, statistical distributions, frequencies of log events, and so on. Whenever one of these detection modules reports an anomaly, then it can either be converted or filtered, and in the end will be outputted, and either on console, which is the most easiest thing and what I will show you later on. We could also forward it via Kafka to a SIEM, for example. We could create new log data for it, or we could also send a summary as an email to the system administrator. Now in the live demonstration, we will have a look at the following components, especially important for the analysis part. I will have a look at value ranges, sequences of events, and also the entropy of values. Okay, this brings us to the first live example, and here's a quick overview. So this one will be about operational technology, and as you can, or here we see in a sample line, and it basically just tells us the number of bytes that were sent in a specific point in time. There will be also other events like the temperature that was measured, or the number of syscalls that were executed. And we do have a training file where only normal events occur, and we then also have a separate file for detecting, and this one contains an attack where someone installed a crypto miner. So hopefully this crypto miner will change one of the values that we measure. Here in the bottom of the slide, you can see an example. So we measure, in this case, the number of bytes sent for different servers. So server 5 has this 149,000 something bytes sent, and so on. And we process all these lines and create this model here in the center, which tells you for each server what the expected range of these values is. And then in the detection phase, you can check for each server again if the values that you observe fall within these ranges, and if they do not, like this one here, then we've detected an anomaly. Okay, let's try this out with the AMiner. So first of all, the AMiner just runs as a script. You can download it and try it out yourself. And first of all, let's have a look at the data that we want to analyze. So this is the log data. As you can see, there is also this number of bytes sent, temperature measurements, and so on. Many different events for many different servers. And we've prepared a configuration for the AMiner, and this configuration will just tell you that, first of all, the learn mode is on, so we are now creating the model that we want to detect. Here we'll just specify the training file that we will use, and then comes all the nodes from the parser, and this is, we've foreseen the parser as this graphical representation, and this is how the AMiner internally represents this parser. Maybe some important part is here the root node of the parser, where you can see first of all comes the timestamp, then a space, then the host name, another space, then the service name, and so on. And for example, we branch into different event types for the temperature, the number of syscores, and the send bytes. For the analysis part, we for once have a parser count, which we just use to tell us how many log lines were parsed, so that we know when the log file is completely processed. And then we have 3 so-called value range detectors that will monitor both the send bytes, the syscores, and the temperature, and create these ranges. And finally, we have an output event handler, which is the stream print event handler, which just gives us the anomalies on the console. Okay, that's all we need to know to start the AMiner. And I will start the AMiner with this -C flag, which just means that I will delete all the models that I've learned before, so it starts from a clean state. And now the AMiner is running, and you can immediately see there are lots of anomalies, and that makes sense because in the beginning we do not have any ranges, or the ranges are very short, so they need to be extended. And the longer the AMiner is running, the less anomalies occur. And after some time, I think now, we've processed all the 100,000 lines that were in this log file, and we can actually have a look at what the AMiner learned. For example, for the send bytes, we have here the minimum and the maximum values of each server. So for example, server 6 has a minimum of 353 bytes sent. We can now use this model and run it on our testing file. So the testing file just looks the same as the training file, but it has somewhere in there the anomaly that we want to detect. And when I will now run the AMiner again, I don't use this -C flag because I want to use the model that we've just learned and not delete it. Now the AMiner processes the file, and hopefully soon, now we have detected an anomaly. And if we inspect this anomaly closer, then we can see that there was one event where the CPU temperature had a maximum value of 67, which is of course way outside the expected range of around 45 degrees. And therefore this event was correctly detected as anomalous. Okay, now we come to the second example. In the second example, we try to detect remote command execution in Apache Access logs. For this, we will analyze the requested resources. Like here you can see we requested with a GET request this WordPress admin site. And the idea is that when you analyze many of these requests, there will be some patterns that are reoccurring. Especially, we have a look at the character distributions of character pairs. And whenever there are many new character pairs, then it's likely that someone tried to do something unusual. So let's have a look at an example again. Here in the bottom left side of the slide, you can see some GET requests to WordPress admin, WordPress content, and so on. And the model that we learn is that for the W, for example, there always follows a P character because this WordPress has this WP sequence. Similarly, for the P, there always follows a dash, and then for the dash, we can either have an A or a C following. Now that's very simple, but if we have many thousands of these requests, then we get a good idea about the character distributions that we expect. And in the test file, we can then see that the same or similar requests are considered normal, while, like, for example, the static evil.php has many strange character pairs and therefore is detected as an anomaly. Again, let's do this with the AMiner. Now this time I will only show you the training file. So these are lots of Apache access requests, and as you can see, they're of course way longer and have way more characters. And the configuration basically looks quite similar to before, except that I added this new detector. Okay, now I got it. So this time the AMiner does not produce that many anomalies because the threshold that we set for detection is very high. But looking again at the model that we learned for these character distributions, we can see that so all these integers represent characters. For example, the 47 would be the slash, which is what almost all log lines or almost all requested resources start with. And the other integers are the frequencies with what this character pair was observed. So again, we run the AMiner with this model on a test file, and hopefully we will detect the anomaly. So since these log files are very short, it does not take a long time to process them. And having a look at this tells us that we, in fact, managed to detect our injection. So here, obviously, this netcat and % signs were very unusual and therefore detected. However, we also see that, for example, there are some false positives. In this case, there was a timestamp in the log event in the value, and since timestamps, especially with that many decimal places, are relatively random, it was also detected. However, so this value, that critical value, was just below our threshold, and as you can see here, for this actual true positive, it was way lower. So we could just adjust the threshold and we would get rid of the false positives. Okay, to the last example. And I will go very quickly over it because time is slowly running out. So this is is about process hijacking. So in audit log files, you always have this syscall equals, and then you see what operation is carried out, like reading a file or writing a file. And the idea is that the sequences in which these operations occur are relatively determined, because you always use applications in a certain way, and then after some time all the possible sequences in which these syscalls occur are observed. So for example, here we have the sequences 0, 1, 2, and then 1, 2, 2. So with a sequence length of 3, we get these 3 sequences, and then whenever in the testing file we observe a new sequence, then it will be an anomaly. Let's again have a look at this in a live demonstration. So the log file this time looks like this. It's an audit log file, and here, for example, the syscall is 0, and then there's 2, and so on. I think you get the idea that there are many sequences. Let's run the AMiner again. So this time the file is way longer, so it will take some time until it's done. So I cannot tell you. Audit logs, of course, have many processes that are interleaving, so that's also something the AMiner has to take care of to untangle these interleaved processes in order to get the right sequences out of it. And here you can also see very well that in the beginning there were lots of anomalies, and now the more lines we process, the fewer anomalies occur. And I think we've now reached the end of the log file. So I can stop the AMiner and run it on the test data set. And hopefully we will also get here the anomaly that we expect. There should be only one anomaly where a new sequence occurs. Exactly, this should be the anomaly. And the sequence that we detected is 2, 1, 0, which apparently never occurred in the training file before and was therefore detected as an anomaly. Okay, so this is already the end of the presentation. So I will now come to the conclusion and the key takeaways that I want you to remember. So hopefully you've seen as part of this presentation that log data analysis is very difficult because there are many different log files, many different formats that you need to parse and that you need to take care of. Also, log data occurs in very high volumes, and it occurs as a stream. So you cannot just apply your traditional machine learning models. You need to write very fast code and also need to use incremental algorithms in order to handle this problem. And with our solutions, ACID and AMiner, we are able to support administrators by generating parsers for log data. We can train models in a semi-supervised manner. We can forensically analyze log data, as I've just shown you in the live demonstration. And of course, you can also detect anomalies in as soon as they occur, as soon as log data is generated, so in a live operation. Here are some important links. Everything we showed you is open source, so please check it out. That would be very cool. And other than that, thank you very much for your attention.
All right, thank you very much. Do we have any questions?
Thank you very much for your talk. I have one question regarding your fast log data parser. What's your approach on multi-line log formats such as postfix logs? Because they are quite, how to say, complicated to parse.
Yeah, well, I think yeah, okay, now it's working. We usually then have to somehow find parts in the log data that basically dissect the log events. So another multi-line format, for example, would be JSON, where it's quite easily. There we have some brackets that basically tell us where the event starts and where it ends. So, but otherwise, it's unproblematic for our approach since it digests the whole event until the point comes where it decides that the event ends, and also the line breaks do not affect it negatively.
So maybe to add, you need to define some delimiter, like for example, it could be a double new line that differentiates the events from each other. So you just don't just have the new line, but a double new line or a semicolon or something. There's usually some delimiter that defines the end of the event.
Thank you very much.
All right, do we have any more questions? Oh, yes.
Yeah, thanks for the talk. I have a question regarding the feature that you can learn from system calls. I have a hard time to believe that this is mostly useful, because this means when you train regarding the system calls, you have to do a full code coverage testing of your application, and when there is an anomaly detected, the system administrator has to know exactly on system call level what the application is doing. And usually they don't even know what files are written, so how can they know about the system calls?
So yeah, of course you're right. It's quite difficult to define when the training phase ends, because, as you say, it's very complex applications. They can have like a high amount of distinct sequences in this example, like in the example I showed you. But we always assume that we have weeks or maybe months where this is running live, and then you will basically know. Let's say in the first week you have lots of anomalies, in the second you have fewer, and at some point it somehow stabilizes. If it does not stabilize, then the model is just not working. So it depends always on the application case, how deterministic the behavior that you are trying to monitor is. If it's not deterministic, like humans always doing something new, you cannot really learn it that way. That's true. But other than that, I mean, especially the Syscore one, it's quite a state-of-the-art approach, which has been used for many years. We just implemented it for the AMiner. So it is useful apparently because people are using it. But it's true that it does not always work. You always need the right application.
Yeah, so another option here would be to use the detector, for example, in an unsupervised way, which means that you never stop learning. And each anomaly in this case would be raised only once. But you can also then say, okay, if you, for example, detected an anomaly, so you have to analyze all the malicious sequences, basically, but you could then remove the malicious ones from the persistency, for example, and modify the model the AMiner uses manually.
We also have a question from the stream, and it's by Martin J. How many different hypotheses are typically applied to or checked for the same events or series of events? So that is user logged in on a server, and then server contacts IPs and bytes and stuff like that.
That's a quite difficult to answer question because it really depends on the system itself and on the configuration. So often we have several detectors that trigger alerts for a single anomaly, for example. So there could be several detectors that trigger an anomaly for only a single line, which means that we often have the problem when we use anomaly detection. So it's not a problem that is there only for the AMiner, but we often have a lot of events generated by anomaly detection, and you often need quite intensive post-processing of these alerts. So we're also working on solutions like an alert aggregation that helps to aggregate such alerts and to reduce the number of events that have to be analyzed by a system administrator, for example.
All right, thank you. We have run out of time. Once again, thank you very much for the great talk. And I think you have something for us?
Yes, sorry, is it on? No. Yeah, one last comment from my side. So this is a very complex topic. There was a very short overview. If you're interested in the topic, with a new book, which you can see here, I also brought some samples. You're free to take them, so I highly recommend that. If you're interested in the topic, please grab one. Thank you.